So this is my lab report for Lab 3 black holes. So to introduce this lab, the purpose of this lab, we had two parts. The first part is we wanted to try and find the mass of the black hole, which we were not given, given the star mass, and then given a net force that we calculated, and also the star position. And then the second part of the lab, we wanted to try and find a velocity that would allow the ship to safely leave the planet and also the black hole without crashing. Some principles I used in this lab was actually splitting the net force into its parallel and perpendicular components, in which the parallel component has p hat times the change in magnitude of p over the change in time. And then the perpendicular component is the magnitude of momentum times the change in p hat over the change in time. We also use the force of gravity in this lab. So we have the big G universal constant times the mass 1 times mass 2 on top, divided by the distance squared. And then we also multiply that by the negative direction of the r vector. And then lastly, we also have Newton's second law, momentum principle, which can be derived into the velocity and position update formulas. And just to talk about some results, my ship was able to leave the system safely and get away from the black hole without crashing. Here is part one, initial conditions and calculation loops. Here is the screenshots I've provided. So here's the big constant. This is the mass of the star we were provided. And then this delta T, the delta T is a day. So I did 60 by 60 by 24 to give me a day. And then I won't talk about every single variable calculation I've done in this loop. I will talk about the important things though and touch on those. So here, like we said, with the parallel and perpendicular splitting the components, we're finding the p hat, then we're finding the change in the magnitude of p over change in time. Multiply those together and we get the parallel component of momentum, or change in momentum, sorry, which is also equal to the net force parallel component. And then to find the perpendicular, what you can do is, because the overall change in momentum is equal to the sum of the parallel and perpendicular components, since we already found the parallel one, we can just subtract it from the total and we'll get the perpendicular component. So, and then those equal, they're the same, momentum and net force. Then to find that mass of the black hole, what I did is from the gravity equation that I had on the previous page, I set the mass of the black hole equal to the rest of the gravity equation. So I had it alone on one side. Here's my video when I actually run the program. So it's calculating a new mass for each delta t. And you can see that this mass is varying as it's an estimate right here. So what I did to try and get a very precise mass of the black hole is I summed all of the black hole mass observations divided by the number of the observations. And I got here 9 times 10 to the 35 kilograms. And then here, once it returned in that orbit to its initial position, this was the net force it had at that position, and then the parallel and perpendicular net force components. As for part two, same thing, I have initial conditions and loop screenshots. So here's the mass that I plugged in from my results of part one. This was all given to us. And then even though it was recommended that the default was 1 hour, 60 by 60, I just did 60 by 20, so only 20 minutes. This gave me enough of a scope to see where the spaceship would go. And then here, so I have the gravity net force here. So this is the force on the planet from the black hole that I've calculated. This is the force on the planet from the ship. You add those up, you get the total force, the total net force, gravity force on the planet. And then here, same thing, but just with the ship. So total force on the ship from the black hole, the force on the ship from the planet, and then the total force on the ship is the sum of these. And then once you have these total forces on ship and planet, you can actually plug them into the velocity and position update formulas for each. And then this was the velocity that I used, that I found best suited, negative 87 for the x direction, 87 for the y direction. That allowed the spaceship to leave the system. So it got very close to the black hole and leave the system without crashing. Some possible sources of error. The velocity that I estimated could be more accurate. It was only done through trial and error. So there might be a formula that might find one that could get closer to the black hole and approximate it a little better. And then second, summing the black hole masses in part one into a very large number in Excel spreadsheets, which is what I did, could have yielded a calculation error that might not be a 100% accurate calculation of that. And then answering the lab report questions, the change in momentum versus the net force. So we can observe the change in momentum, but we cannot observe a net force because we would need to know the agents acting on the system. That's the difference in those. And then, yes, the ship can orbit, and it orbited with these speeds given right here.